Welcome to Unacademy GATE ESE ME. This is Umamaheswara Rao. This is a super talent batch for Engineering Sciences XE. Complete maths will be covered by myself. Complete technical subjects by JS Gill. Detailed coverage of GATE XE syllabus with handwritten notes. Myself Umamaheshwar Rao, Faculty of Engineering Mathematics for GATE and ESE, educator at Unacademy. I have 21 plus years of teaching experience. I have guided more than 1 lakh students. Unacademy presents Padho Khelo Crack, Land with Top Educators from July 1st to 30th. Concept based learning for each subject. Take a quiz, check your preparation, top the leaderboard and get featured on YouTube channel. Enroll now. Unacademy GATE and ESE presents free classes by myself, Umamaheshwar Rao. Unacademy GATE and ESE Majorly Compact 2.0 Guaranteed Scholarship Test in Mechanical Engineering, Civil Engineering, Electrical Engineering, Electronics and Communication Engineering, Computer Science and Information Technology. 20 questions, 60 minutes. Rank 1 scholarship 90%, rank 2 to 5 scholarship 70%, rank 6 to 15 50% scholarship, rank 16 to 50 30% scholarship, rank 51 to 200 25% scholarship. Test will be conducted on July 17th at 12 p.m. Enroll for free. Unacademy GATE and ESE Majorly Compact 2.0 Guaranteed Scholarship Test. Test will be conducted on July 17th at 12 p.m. Enroll for free. Unacademy is announcing Lakshya batch for GATE 2023. Batch commences from July 14th. Unacademy is announcing Pragati batch for GATE 2024. Batch commences from July 14th. The features of Unacademy subscriptions: top educators, doubt clearing sessions, raise a hand option, study notes, test series. The physical notes is available for Iconic subscribers, 1:1 live mentorship program, strategy and study program, live audio interactions during open house for Iconic subscribers. Unacademy Plus offer for GATE and ESE, Mechanical Engineering and Chemical Engineering, Computer Science and Information Technology, Electrical and Electronics Engineering, Civil Engineering. Save up to 38%, valid till July 14th. Use code KUR75. Unacademy GATE and ESE yesterday I have explained eigenvalues and eigenvectors, how to calculate eigenvalues and eigenvectors. Today I would like to discuss properties of eigenvalues and eigenvectors, Cayley-Hamilton theorem and diagonalization. Lecture 8. Lecture 8 on matrix theory. The properties of eigenvalues and eigenvectors. The sum of eigenvalues of a square matrix, the sum of eigenvalues of a square matrix is equal to the sum of eigenvalues of a square matrix is equal to the trace of the matrix. the sum of eigenvalues of a square matrix is equal to the trace of the matrix. The product of eigenvalues of a square matrix is equal to determinant value of the matrix. The sum of eigenvalues of a square matrix is equal to the trace of the matrix. The product of eigenvalues of a square matrix is equal to determinant value of the matrix. Next one. Good afternoon, Rajesh. Good afternoon, Abhishek. His voice is fine. Abhishek. All right. Next one. The eigenvalues of A and A transpose are the eigenvalues of A and A transpose are always same. The eigenvalues of A and A transpose are always same. The eigenvectors of A and A transpose are not same. The eigenvectors of A and A transpose are not same. You have to remember this point. Eigenvalues of A and A transpose are same, but eigenvectors of A and A transpose are not same. The eigenvalues of a triangular matrix or diagonal matrix. Eigenvalues of a triangular matrix or diagonal matrix are its leading diagonal elements. If the matrix is triangular or diagonal, the eigenvalues are its leading diagonal elements. For example, if you take matrix A 2 3 5 0 6 9 0 0 7, now the characteristic equation is determinant of A minus lambda I equal to 0. That is determinant of 2 minus lambda 3, 5, 0, 6 minus lambda 9, 0, 0, 7 minus lambda equal to 0. See, determinant value of triangular matrix is always product of its leading diagonal elements. That's why 2 minus lambda multiplied with 6 minus lambda multiplied with 7 minus lambda equal to 0. That implies lambda equal to 2, 6, 7. These are nothing but its leading diagonal elements. That's why eigenvalues of a triangular matrix or a diagonal matrix are its leading diagonal elements. Understood? Next. Next point. If 0 is, or 1 minute, A is a singular matrix, A is a singular matrix if and only if at least one of its eigenvalue is 0. If A is a singular matrix, then at least one of its eigenvalue is 0, because singular matrix means determinant value 0. Determinant value is nothing but product of its eigenvalues. Product of its eigenvalues equal to 0 means at least one of the eigenvalue must be 0. If all the eigenvalues of a square matrix, if all the eigenvalues of a square matrix are non-zero, if all the eigenvalues of a square matrix are non-zero, then A is non-singular. Then A is non-singular matrix. If all the eigenvalues of A are non-zero, then A is non-singular matrix. If the matrix is non-singular, all its eigenvalues are non-zero. Next property. If lambda is an eigenvalue of, if lambda is an eigenvalue of non-singular matrix, if lambda is an eigenvalue of non-singular matrix, then first point, 1 by lambda is an eigenvalue of, 1 by lambda is eigenvalue of A inverse. Second point, Det A by lambda is an eigenvalue of adjoint of A. So, if lambda is an eigenvalue of non-singular matrix, then 1 by lambda is an eigenvalue of A inverse. Det A by lambda is an eigenvalue of adjoint of A. Next property. If lambda is an eigenvalue of a square matrix A, if lambda is an eigenvalue of a square matrix A, then first point, lambda square is an eigenvalue of matrix A square. Lambda cube is an eigenvalue of A cube. Lambda power m is an eigenvalue of matrix A power m, where m belongs to n, natural number system. M belongs to n for any positive integer m. That means lambda square is eigenvalue of A square, lambda cube is eigenvalue of A cube, lambda power 4 is eigenvalue of A power 4, like that. Next. K lambda is an eigenvalue of Ka. K lambda is eigenvalue of Ka, where K is a scalar. Next one. Fourth one. Lambda plus K is an eigenvalue of A plus Ki. Lambda plus K is an eigenvalue of A plus Ki. Lambda minus K is an eigenvalue of A minus Ki. Lambda minus K is an eigenvalue of A minus Ki. Lambda square plus C1 lambda plus C2 is an eigenvalue of A square plus C1A plus C2I. A square plus C1A plus C2I. Lambda square plus C1 lambda plus C2 is an eigenvalue of A square plus C1A plus C2I. If A plus IB is an eigenvalue of A if A plus IB is an eigenvalue of A, then A minus IB is also an eigenvalue of matrix A. So if A plus IB is an eigenvalue of A, compulsory A minus IB is also an eigenvalue of A. So the complex eigenvalues appear pairwise. Now the eigenvalues of A Hermitian matrix, the eigenvalues of a Hermitian matrix or a symmetric matrix. The eigenvalues of a Hermitian matrix are a real symmetric matrix, a real symmetric matrix are always real. The eigenvalues of a Hermitian matrix or a real symmetric matrix are always real. The eigenvalues of a skew Hermitian matrix or a skew symmetric matrix are either zero or purely imaginary, either zero or purely imaginary. The eigenvalues of a skew Hermitian matrix or a skew symmetric matrix are either zero or purely imaginary. The eigenvalues of an orthogonal matrix, the eigenvalues of an orthogonal matrix are a unitary matrix, have absolute value 1, absolute value 1, that is mod lambda equal to 1, that is mod lambda equal to 1. The eigenvalues of an orthogonal matrix or a unitary matrix have absolute value 1, that is modulus value 1. Next one, the eigenvectors of a square, a cube, a power n, the eigenvectors of A inverse, adjoint A square, A cube, A power 4 and so on are always same. The eigenvectors of A inverse, adjoint A square, A cube and so on are always same. In a square matrix, if n rows are identical or proportional, then n minus 1 eigenvalues in a square matrix, if n rows are identical or proportional, then n minus 1 eigenvalues will be 0. In a square matrix, if n rows are identical, then n minus 1 eigenvalues will be 0. For example, matrix A is 1 1 1 1 1 1 1 1 1. 3 rows are identical. Since 3 rows are identical, therefore 2 eigenvalues are 0. Third eigenvalue is 3. Because sum of all elements of first row 3, sum of all elements of second row 3, sum of all elements of third row 3, therefore compulsory sum of all elements of each row is same. That sum will be one of the eigenvalue. So 3 is one of the eigenvalue. Since 3 rows are identical, therefore 2 eigenvalues are 0. 2 eigenvalues are 0, 1 eigenvalue is 3. Next. The eigenvectors corresponding to distinct eigenvalues of a symmetric matrix is always orthogonal. Orthogonal means perpendicular. The eigenvectors corresponding to the distinct eigenvalues of a real symmetric matrix are always orthogonal. For example, matrix A is 4 2 2 4. Matrix A is 4 2 2 4. The eigenvalues are 6 and 2. The eigenvalues are 6 and 2. The eigenvector corresponding to eigenvalue 6 is 1 1. The eigenvector corresponding to eigenvalue 2 is 1 minus 1. Now we have to check whether these eigenvectors are orthogonal or not. How to check whether vectors are orthogonal or not? If the dot product between these two vectors is 0 or not. If dot product between these two vectors is 0, we can confirm that these eigenvectors are orthogonal. Now x1 transpose dot x2, x1 transpose 1 1, x2 transpose 1 minus 1. If we calculate dot product, row multiplied with column, 1 minus 1, that is 0. x1 transpose dot x2 equal to 0. Therefore, x1 and x2 are orthogonal. x1 and x2 are orthogonal. Next one. If all the leading minors, if all the leading minors of a real symmetric, if all the leading minors of a real symmetric matrix are positive, then all its eigenvalues are positive. If all the leading minors of a real symmetric matrix are positive, then all its eigenvalues are positive. For example, matrix A is 2 1 1 5. It is a 2 cross 2 matrix. For a 2 cross 2 matrix, there are only 2 leading minors. 1 cross 1 leading minor is, this is 1 cross 1 leading minor. That is 1 cross 1 leading minor. So 1 cross 1 leading minor is 2. That is positive. 2 cross 2 leading minor is 2 1 1 5. 2 1 1 5. Ten minus 1, 9, positive. So 1 cross 1 leading minor is positive. 2 cross 2 leading minor is also positive. Therefore, compulsory eigenvalues of this matrix will be positive. Verify. Determinant of A minus lambda I equal to 0. Determinant of 2 minus lambda 1, 1 5 minus lambda equal to 0. That is 2 minus lambda into 5 minus lambda minus 1 equal to 0. That is 10 minus 2 lambda minus 5 lambda plus lambda square minus 1 equal to 0. Lambda square minus 7 lambda plus 9 equal to 0. From this we can write lambda is equal to 7 plus or minus square root of 49 minus 36 by 2a, that is 7 plus or minus root 13 by 2, 7 plus root 13 by 2, 7 minus root 13 by 2, 7 plus root 13 by 2 is 5.3, 7 minus root 13 by 2 is 1.69, both are positive. 5.3 is positive, 1.69 is also positive. Since both are positive, therefore eigenvalues are positive. If all the leading minors of a real symmetric matrix are positive, then all its eigenvalues are positive. Next property. The eigenvectors corresponding to the distinct eigenvalues of A, the eigenvectors corresponding to the distinct eigenvalues of any square matrix are always linearly independent. The eigenvectors corresponding to the distinct eigenvalues of any square matrix are always linearly independent. If the matrix is square, eigenvalues are distinct, then eigenvectors are always independent. For example, if the matrix is 3 cross 3, suppose the eigenvalues of A are 2, 5, 9. Corresponding to eigenvalue 2, there is one independent vector. Corresponding to eigenvalue 5, there exists one independent eigenvector. Corresponding to eigenvalue 9, there exists one independent eigenvector. So, for every distinct eigenvalue, there will be one distinct independent eigenvector. That is the meaning of this statement. Next one. The eigenvectors corresponding to repeated eigenvalues of any square matrix the eigenvectors corresponding to repeated eigenvalues of any square matrix may be linearly independent or may be linearly dependent. May be linearly independent or may be linearly dependent. The eigenvectors corresponding to the repeated eigenvalues of any square matrix may be linearly independent or may be linearly dependent. For example, yesterday I have explained you this problem. 2 0 0 0 2 0 0 0 2. Corresponding to this matrix, the eigenvalues are 2 2 2. Eigenvalues of A are 2 2 2. The eigenvectors are 1 0 0 0 1 0 0 0 1. Now if we verify these three eigenvectors, determinant value is 1, non-zero. If determinant is non-zero, the three eigenvectors are linearly independent. Three eigenvectors are linearly independent. So matrix is square. All three eigenvalues are repeated. For the repeated eigenvalues, we got three independent eigenvectors. So that's why the eigenvectors corresponding to the repeated eigenvalues of any square matrix may be independent or may be dependent. In this example, we got independent. In some other example, we may get dependent. I'll give another example. For example, A is 1 0 0 1 1 0 1 1 1. In this case, eigenvalues of A are 1 comma 1 comma 1 because it is a triangular matrix. In the case of triangular matrix, eigenvalues are nothing but leading diagonal elements. Now, if you calculate eigenvector, there is only one independent eigenvector. There is only one independent eigenvector. See, the eigenvalues of A are 1 1 1. One eigenvalue repeated 3 times. So algebraic multiplicity of eigenvalue 1 is 3. But there is only one independent eigenvector. There is only one independent eigenvector. So only one independent eigenvectors means the remaining are dependent. Therefore, the set of eigenvectors is linearly dependent. So the eigenvectors corresponding to the repeated eigenvalues of any square matrix may be independent or may be dependent. In the previous example, we got eigenvectors are independent. In this example, we got eigenvectors are dependent. The set of eigenvectors dependent because at least one eigenvector is dependent, the set is dependent. That's why in the case of repeated eigenvalues, the eigenvectors may be independent or may be dependent. Next property, Cayley-Hamilton theorem. Every square matrix satisfies its characteristic equation. Every square matrix satisfies, every square matrix satisfies its characteristic equation. Every square matrix satisfies its characteristic equation. This is known as Cayley-Hamilton theorem. For example, matrix A is 1, 2, 3, 4. First we have to find characteristic equation of A. Determinant of A minus lambda I equal to 0. Determinant of 1 minus lambda 2, 3, 4 minus lambda equal to 0. Now 1 minus lambda multiplied with 4 minus lambda minus 6 equal to 0. That is 4 minus lambda minus 4 lambda plus lambda square minus 6 equal to 0. That implies lambda square minus 5 lambda minus 2 equal to 0. That is called characteristic equation of A. Now we have to prove that the characteristic equation is satisfied by the matrix. That's why I am calculating A square minus 5A minus 2I. So I have to calculate A square minus 5A, 5 multiplied with A, 5, 10, 15, 20 minus 2I, 2002. So now I require A square. A square is given by A into A. That is 1, 2, 3, 4 multiplied with 1, 2, 3, 4. Simplify this. Row multiplied with column. 1 plus 6, 2 plus 8, 3 plus 12, 3 2 ja 6 plus 4 4 ja 16. That is 7, 10, 15, 22. 7, 10, 15, 22. Simplify this. 7 minus 5 minus 2, 0. 10 minus 10 minus 0, 0. 15 minus 15 minus 0, 0. (22 minus 22, 0). Clearly, A square minus 5A minus 2I equal to 0. Therefore, A square minus 5A minus 2I equal to 0. So clearly the characteristic equation is satisfied by the matrix. So every square matrix satisfies its characteristic equation. Next one, diagonalization. When we can say a matrix is diagonalizable. When we can say a matrix is diagonalizable if for a given matrix A, for a given matrix A of order n, for a given matrix A of order n, there exists a non-singular matrix. There exists a non-singular matrix P. There exists a non-singular matrix P such that P inverse AP equal to diagonal matrix D, then A is called, A is said to be, then A is said to be diagonalizable. A is said to be diagonalizable for a given matrix A of order n. If there exists a non-singular matrix P such that P inverse AP equal to D, then A is said to be diagonalizable. You can say in another way, a matrix is said to be diagonalizable if the geometric multiplicity and algebraic multiplicity of each eigenvalue coincides. A matrix A is said to be diagonalizable if the algebraic multiplicity and geometric multiplicity of each eigenvalue coincides. The algebraic multiplicity and geometric multiplicity of each eigenvalue coincides, you can say that the matrix is diagonalizable. What is the process of diagonalization? Working rule. First we have to find eigenvalues of A. Eigenvalues of A. Step 2. Find eigenvectors of A. Find eigenvectors of A. Suppose A is 3 cross 3. Find eigenvalues of A. Lambda 1, lambda 2, lambda 3. Find eigenvectors of A. x1, x2, x3. Step 3. Write model matrix P. Model matrix P is nothing but collection of 3 eigenvectors x1, x2, x3. Write x1, x2, x3 in one matrix. Step 4. Find P inverse. Find P inverse. Step 5. Calculate P inverse AP. P inverse AP is nothing but diagonal matrix D. See, this diagonal matrix D is nothing but lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. The eigenvalues of matrix A will be present in the leading diagonal of this diagonal matrix. This process is known as diagonalization. So compulsory you will get the eigenvalues of matrix A as leading diagonal elements of this diagonal matrix D. This process is known as diagonalization. Understood? Tomorrow I am going to discuss problems related to eigenvalues and eigenvectors, Cayley-Hamilton theorem and diagonalization. Thank you. I am going to complete engineering mathematics for XE in this batch. Same timing, 12 to 1 daily. Thank you.